Okay, now we talk about the, I think the last part, item number 5, which is called as a batch normalization. Okay, so what is batch normalization? Okay, that is related to this slide. Okay, batch normalization. Yep, this one, batch normalization. So batch normalization is a process, one of the process that involved in your CNN for the purpose of applying or doing a pre-processing on your data. Okay, so before we talk about that one, let's discuss about what is normalization is it first, because otherwise you will not understand why we need to do the batch normalization. Okay, I just managed to write up all the things there in my whiteboard there. So what is a normalization? Okay, don't read this one. What is a normalization for you? I think based on what we understand, normalization is something when you want to make it the element standard. Okay, elements standards, meaning that if you have a set of number and you find out the number is has a very or is have a different range of scale. Okay, let's say you have set of number. For example, I have some numbers like this one. Okay, you have one number x1. Okay, I put it x1, x2. Okay, just put this. Okay, the first number of x1, let's say 0.1. Okay, and then you have another set of x1 when you okay, your x2, let's say 10, and then you have another set number 0.2, and this one is maybe 15, and this one is 0.8, and this one should be might be 80. So you find out this number, their range is in a floating number. The range, it might be from, if you see the numbers there, I can conclude that the number might be from 0 to, might be, because you have a 0.8, I assume just the maximum can be, it should be 1 there. But this one, the minimum is 10. Okay, maybe it start with 1. I assume it start with 1, and the scale is can go, or the range there can go up to 100. Just assume that, because we just consider that this x2 set of number, the number is in this range, but this set of number in this range. So you can see there, the range is not similar. Okay, once the range is not similar, it's not appropriate to, you know, to attach this x1 x2 together in one matrix, because later other, doesn't matter what type of operation, this one will be dominant because it will have a lot big value. So that's why normally that is where in mathematics they always apply what we call as a normalization. Okay, once you apply the normalization, then if you apply normalization to x1, then you will end up with the scaling from 0 to 1, and then if you apply the normalization of this one, then you will end up with the set of number of scaling with 0 to 1. So then it will be fair to add to you know to combine between x1 and x2 in one matrix. Okay, so that is the purpose of normalization in general. So by having a normalization, then you just remind in your mind, you just remember in your mind is that is for the purpose of convert any number with different scaling or different range into a standard range which is from 0 to 1. Okay, but it's not just 0 to 1. Actually, you will see later, it's not just 0, the range is 0 to 1, but one of it is 0 to 1, the range. Okay, if you convert any value and then you change the element into the format where you have only a number which is in between 0 and 1, that is the meaning by normalization. So from the normalization, okay, now in machine learning they call this normalization operation is always related, I'm sorry, in machine learning the normalization is always related to what we call as a feature normalization. I think the concept is similar. Okay, it still talking about x1 and x2 in this example, meaning that if you relate with this example, you just assume your x1 is your feature number 1, this one is your feature number 2. Okay, and then you just assume this is your, you just assume this is your first sample, this is your second sample of your training data, and this is your third sample of your training data. So again, if you fit these two numbers into your neural network, or doesn't matter is it a neural network or other machine learning, it's still not fair if you don't do the normalization, because later this one will dominant. Okay, just assume that let's say we talk about your first lecture on this thing, which is linear regression. Okay, again, what is the linear regression? Then you will have what? Do you use the y? I just put the y there because I also forget the notation there. I just remember the theta. You use the theta 1. I'm sorry, theta 0 plus theta 1 x1 plus theta 2 x2. So imagine that this 0.1 going into that side, which is your x1, this 10 going into that side, which is your x2. So because your 10 here is very big, then this element will dominate this expression. Okay, because this one you have x2 which is biggest. So that's why that is the things that people in machine learning community concerned about. That's why one of the proper way or a good way to train a data is to apply a pre-processing, and one of the pre-processing that always we do in our data is by applying a normalization, or in other words is called as a feature normalization. So you need to convert your data into this range. Doesn't matter is it x1 or x2, you must convert into this range. Once you have this range, then you proceed with the training your model by using this normalization data. Okay, so that is the reason. So in order for you to convert this one into this range, or to apply the normalization, you have a two type of normalization. You can apply what we call as min-max normalization, or you can apply a mean normalization. The min-max normalization, this one for sure that you will get the normalization value which is in this range, which is from 0 to 1. Okay, this is the formula. So don't worry about the normalization, because I just want to give you some exposure. That's why I come up with all this calculation, and you just take it as the additional knowledge, because this will not be asked in your exam. Okay, just additional knowledge before I go to the batch normalization, because again I promise to you that in deep learning we just learn the concept. Okay, the calculation is not very big, so that's why the calculation is just small. So normalization will not counted in calculation. Just make sure that you can understand the concept of batch normalization. So you can apply min max normalization, or you can apply mean normalization to do the normalization. Okay, but for the mean normalization, I think you cannot get the range from 0 to 1, but you can get from negative n to n, where the n is actually always less than 1. Okay, but it's a standard. You will get something, some value, but the value have the range from negative value to positive value, but the negative value is not more than 1. Okay, by applying this formula. So that is the normalization. Okay, this is happen even in any machine learning. It's not just deep learning. In any machine learning, normalization is better to do in practice, because you will avoid imbalance scaling, because x1 has a small scale, x2 have a bigger scale. So that's why normalization is something which is essential. Okay, so that is what happened if you have imbalance scaling. You just imagine that this is your x1. Okay, because the range is from here. I think this one is the minimum value up until this point. Okay, it's a very narrow range, but this one represent your x2. Is very wide range. The scale is very wide range, so you have imbalance there. So that's why if you apply the normalization, hopefully you will can get a standard there. It's balanced. So this one is might be for example -1 to +1, and this one is -1 to +1. Okay, so in this I think in this example they are using average normalization, so that's why the scaling is from minus to positive. It's not from 0 to 1. Okay, just skip this slide. So in CNN we also use the normalization in designing the architecture. Remember that let's go back to the first item there. The one that show you the architectures. Yep, this one. Okay, I already talked to you about the basic operation happen in CNN. Okay, normally this is a convolutional layer, this is a pooling layer, and then you have a fully connected layer, and on this side, okay, again convolutional layer, maximum pooling because this is subsampling, and then you have another convolutional. So in other words, you have three main layer. One is a convolutional layer, the second one is pooling layer, the last one should be the fully connected layer. And then convolutional and pooling layer, you can play around, you can alternate it, or you can also have a convolution, pooling, convolution, pooling. So you can arrange that in any way that you like, but you must end up with fully connected layer. So that is the CNN. But where actually happen, where is actually the normalization happen is actually in general, normalization always happen is either at this part, means that before you feed this input pixel to your convolutional layer, sometimes people will put normalization at this part. Okay, before the normalization, before the convolution layer, and most of the time, okay, normalization happen is either between inside the convolution layer. Okay, remember that your convolution layer, you will have convolutional operation, and then after you get the output, you apply the activation function before you produce your O matrix. Normally, normalization can also happen most of the time at this position or after this operation, meaning that normalization can be applied before you feed your data into activation function, or you can also apply the activation function first to produce your O matrix, and once you get the O matrix, you apply the normalization to your O matrix here to get the normalization of your O matrix. I just put O head like that to represent my matrix normalization O matrix there. Okay, so in CNN, that is another additional operation need to be involved in your convolutional layer. Okay, you can put your activation your normalization operation before you apply activation function, or you can apply the normalization after you apply the activation function. And you can also another additional things that you can also apply the normalization at the beginning of the CNN, where you need to normalize your input image, meaning that before you feed this input image into your convolutional layer, you apply first your you apply the normalization first to that image. That is another position that you can also apply the normalization. So in this slide, show you some example of well-established CNN and the position where the normalization happen. Where is it? Yep, this one. Okay, for example, AlexNet that we later will discuss. Again, this is the one of the well-established CNN. They using a mean normalization, and then this mean normalization is applied to the input image before you feed into the AlexNet network. Okay, so this is an example, because they want to make sure that every value here have been scaled into minus something and positive something. And another example is VGNet. Okay, this is another well-known CNN. They also apply the mean normalization, however it's a little bit different from the AlexNet. What is the difference between this and this? Both apply mean normalization, but for AlexNet, the input is color image. Okay, you remember it's a color image. It's a 32 times 32. The input size is standard 32 times 32 times 3. Okay, times 3. The depth here is equal to 3 because you have a RGB. That's why the depth equal to 3. So in other words, if you combine RGB together, it's look like a 3-dimensional matrix. So what the AlexNet do, they need to find the average, okay, or the means. Okay, average and mean is the same thing of this whole matrix. Once you find it, then you apply this formula. Okay, you apply this formula that I draw there. Yep, this one. And then each element inside that 3D matrix need to minus with the average or the mean, and then you do that, then you get the normalized version. So that is AlexNet. But for VGGNet, it's a little bit different there. Okay, it depends on the channel. What is the meaning by that? Again, VGNet also the input is RGB, but I forget the size, but this RGB. You have a 3 layers there, or 3 channels, but the difference between LXNet normalization and VGGNet is that VGNet separate this RGB into 3 different channel or 3 different matrix. Okay, it just take this one separately into that one. Okay, this one is this one, and this one is this one. Okay, but in order to find the mean normalization, what the VGG do is that they just find the average of mean of this matrix. Okay, find the average, and then in order to convert this layer into normalization, they just use the same formula, but the average is the reference average is only considered on this matrix only, a single channel. Same with this one, you will find its own average. Once you get the average, you will convert this into normalization value by using the average of this matrix. Okay, and this one, they have their own average, and then from that average you find your own normalization value according to this average. So that is the VGG do. So that's why they call it a subtract per channel means. It's an average normalization, but with respect to average of each channel. Okay, it treat one channel as one average, but this one, the average is 1 because it treat everything in single 3-dimensional matrix. Okay, that is the difference. So that this is some or a few example of normalization happen at the well-established CNN. But okay, just skip this one because I just promised to you that in the previous chapter we will not discuss about the wake initialization. We just assume that our wake will randomly selected, but you can just read it for your additional knowledge. Normally the wake initialization is one of the issue because if you don't select the proper initialization wake, then you will not you will not find the best performance of your designed or your design CNN architectures. Okay, so that's why there's a proper way to find the wake, but in our syllabus we just assume that the wake initialization is done randomly. Okay, but of course in practical it's not randomly. There's some formula to make it you are choosing the initial wake in a proper way. Okay, just go again. We talk about the normalization. So batch normalization is always again it's the same as a normalization. Just to call it as a batch normalization is the one that always happen. Okay, batch normalization is always happen at this one that I discussed in this slide there. Yep, this one. So batch normalization in CNN, they apply there's a lot of normalization, but the most common one is batch normalization. And normally batch normalization in practical it always be need to be put either at this point and this point that I discussed before. It can be after the convolutional operation or after the activation operation. Okay, that is where people always put a batch normalization. So what is the difference between batch normalization and the other normalization that I talked before? Actually is almost similar, but the difference is just the average. Okay, where actually you calculate the average, because average is the one that you the reference average is the one make the average normalization have their different name. For example, that I discussed before in this slide. Okay, where is it? Yep, this one. Yep, this one. So you can see that doesn't matter is it LXNet or VGGNet, they are actually implementing the mean normalization. A batch normalization is also one of the mean normalization, but as you can see that what is the difference there? Every CNN apply the mean normalization, well established CNN apply the mean normalization, but for LXNet, the mean normalization, the reference average is the average of the whole matrix. But for VGGNet, the reference average to compute the average normalization is per channel matrix. Okay, so another normalization which is I said well known and common as compared to this one and this one is what we call a batch normalization, is also implementing the mean normalization, but the or the average normalization, but the average now is the reference average is come from the batch average. Okay, so do you remember batch gradient descent? Is it yeah, batch gradient descent. So what is batch gradient descent? When you have a full batch of your data set, let's say this is your data set, a full training data set, so we call it as a one batch. Okay, that's why you have a batch gradient descent, because you update W based on after you do iteration, fully iteration, after you complete one cycle of or one epoch, then you update your W. So that's why they call it a batch gradient descent. So that the word that batch is also related to this one. What is batch normalization? Assume this is your data set. Of course, our data set right now is not a one-dimensional numbers there, because we have image. Okay, just assume this one sample here is actually an image, and then you have another image, and then you have another image. So going into that direction, actually you have one batch of image. Okay, one batch of image. You assume this is your one batch. This is your one batch image. So what is the meaning by batch normalization is that if you talk about the mean normalization, is that the average, to get the reference average, you need to find the average of the whole image here. Okay, meaning that you assume you have a 3D matrix like this. Okay, this is the image, and then you have a if you have of course if you talk about the color image, you have RG and B there. Okay, that's why you have a 3, the size of depth there is 3. But if you merge or concatenate all batch of image along this way, okay, then you will create one big matrix like this. One big matrix like this that represent a batch of image. So in order to find the batch normalization, then you need to get the average of this whole matrix. So that is meaning by batch normalization. Actually, it's not actually it depend on the how you train. Okay, if you talk about batch gradient descent, This is what we call as a batch normalization. But if you talk about mini batch, where remember if you have a mini batch gradient descent, is that this is the one that always common to deep learning. They always use a mini batch gradient descent, where they separate their data set into several batch. Okay, let's say I separate my data into 4 batch. Actually, the total is, assume this one line represent your image. Okay, image number 1, so you have 100 image. So I separate into 4 batch, meaning that 4 same size image, a same size batch. So you have 25, 25, 25, 25. So if you using the mini batch gradient descent, then your batch normalization is only to find the batch the average normalization, then the average should be only this for this 25 image. Okay, so that's how it's work. Okay, that is the meaning by batch normalization. Then this about just the different they gave the name different because it depend on how you define your average. Is it per channel, is it the whole image, or is it the whole batch? So for batch normalization, the average is the whole batch. So that's why if you talk about the batch gradient descent, but if you apply the mini batch gradient descent, that mini batch which is 25, that in that set you need to find the average value to find the batch normalization. So that is the difference. So just I talk about the concept. Again, I will not go into the calculation. You don't have to worry about that. And then okay, the question is why we don't discuss normalization during the ANN. Why this is very crucial to talk about normalization, especially a batch normalization in CNN. Why do we don't have this in ANN? That is because during our ANN, again, it's related to activation function. Actually, this why batch normalization is very crucial in CNN, because of the activation function. Because in ANN, like I said before, the most common activation function to be used with CNN is sigmoid. If you see the sigmoid function there, you have this function have one characteristic which is called a bounded output, meaning that doesn't matter the input is going into infinity. Okay, again your x-axis here is infinity, x here if you're going towards infinity, the y-axis there is still 1. Okay, it's still 1. You go into that direction, is still 1, because this one is always going to that. So that's why doesn't matter you go into that direction or minus x or positive x going towards infinity, you get 1. So that means you have bounded outputs. But how about ReLU? ReLU, if you going into that direction, going towards infinity, the y also going towards infinity. So meaning that after applying convolutional layer, if you don't have if you don't have a batch normalization, then your O matrix will have a scale which is depend on the data of the input of that convolutional layer. Okay, in some matrix element it can be big, some matrix element can be too small. So that's why you cannot control this value because of the bounded output at the activation function. So that's why, in order to avoid anything dominant at the next layer, for the next layer, because if you have imbalance scale in your matrix and you pass to the next layer, then it will affect the whole network. So that's why in order to control this, one way to control is by introduce with batch normalization, because if you apply the batch normalization, doesn't matter after the convolutional or after the activation operation, it will make the imbalance scale matrix number into a standard or a normalized matrix element before you fit into the next layer. Okay, so that's why batch normalization is very crucial in this topic CNN, because of it's related to the ReLU, because ReLU is the one that we very common in CNN, and ReLU itself is a unbounded output. Okay, what is meaning by unbounded output? Because if your input is going to infinity, the output also going to the infinity. But this one, for sigmoid, that does not happen. It's a bounded output, because if the x going to the infinity, the y still equal to 1. Okay, so we don't have to issue on that. That's why, and in ANN we don't have to use a normalization. So again, this is the, like I said before, you can apply your batch normalization after the convolutional operation. Okay, meaning that before the convolutional or after the activation operation, and again you can also apply it for the fully connected layer at the end part also to normalize your value. That is also can be done. That is also another position that you can apply the batch normalization.